chapter 20, section 3. This is the last section for this chapter. So electric circuits. An electric circuit is a complete path that charge can flow through. You have circuit diagrams that will show you the path of this circuit, how it's flowing, the direction. You'll have some symbols that represent your voltage source. You'll have other pieces such as resistance in there, some devices that will measure the current or measure the voltage that's going through. You might have some light bulbs that are in this diagram, and we'll take a look at a couple of diagrams when we do the review for the notes. There are two types of circuits. There's series and parallel. Series means that it only has one pathway that it can follow through, and when it's flowing through this pathway, it has to hit everything that's in that path. So for example, if you have a strand of Christmas lights that are from a few years ago, they would be on a series circuit. So those, if you had one light bulb or one of those little lights burn out or blow its fuse, the entire strand would go out. And you would have to sit and go through every single one of those bulbs to figure out which one it was. So if one thing stops working, the entire thing stops working. However, today's strands of Christmas lights are now on a parallel circuit, which means they have more than one pathway to follow through. So at least two, if not more than that. So that means if one stops working, the rest of it can continue working just as if that one was still working or not. So that one does not matter. So with parallel circuits, if one stops working, the rest is still going to operate just fine. Now, we've talked before about about power. We're going to specifically talk about electrical power today. So when it comes time for your midterm and your final exam, please be careful as to whether it's talking about electrical power, so with voltage and amps, or if we're talking about mechanical power where we have energy, work, or time. So it's a rate that you have electrical energy being converted. And we measure that, of course, in watts because it's still power. And we're still going to use capital P in our formula. So we calculate this by multiplying the amps, your current, and your voltage. So P equals IV. Let's take a look at an example really quick. An electric oven is connected to a 240 volt line, and it uses 34 amps of current. What is the power used by the oven? Well, our formula, P equals IV. I, that's our current, so 34 amps. V, that's our voltage, 240 volts. 34 times 240, you should get 8,200 watts. Now, if I wanted this number in kilowatts, and I may ask you to do that on several of your example problems in your assignment, you would simply take your decimal and move it 3 places to the left and get 8.2 kilowatts. That's just a little bit of conversion back from the very first chapter that we did that you have in your notes. Practice problem, and I expect you to put this in your notes. A clothes dryer uses about 27 amps of current from a 240 volt line. How much power does it use? Now when you solve this, I want you to write it down in your notes, and I want you to circle it so that when I come around to do a note check for chapter 20, I can clearly see that you did answer this question. Now, something else I want to talk about is electrical safety. All new houses have to be inspected for the correct wiring, for making sure everything is up to code. But correct wiring is not enough. You need fuses, circuit breakers, you need some insulation, you need something to ground out what you have there. So if we look at fuses, that prevents an overload in a circuit. So if you blow a fuse, it's kind of like melting it down because something is moving too quickly, and it causes it to overheat. So it blows the fuse and you have to replace it. Now with circuit breakers, if you have too many things plugged in at once, you have too much current going through that breaker, and so it's going to trip the breaker and turn it off so that the current stops flowing. So for example, if you were to have, let's say, the dryer, maybe a straightener or a curling iron, maybe your hair dryer's going, you have all these things plugged in, it's going to overload the circuit breaker and it's going to trip that and turn it off. It says, hey, you've got too much stuff going, that's a hazard. So you have to go back to the circuit breaker, flip it back on. In insulation, you guys know what insulation is. We've talked about insulators. And then, of course, grounding is when you have excess charge that's being grounded or put into a point that kind of levels it out. And you have, in your safety outlets, you have ground faults that will automatically kind of ground something out and keep that current down. And that's it for Chapter 20.